For decades, the dream of connecting everyone everywhere has inspired innovation in wireless technology. Today, that vision is closer than ever. Qualcomm Technologies is at the forefront, advancing mmWave non-terrestrial networks to expand coverage and capacity beyond what is possible, with the narrower bandwidths in sub-6 GHz spectrum. Now, by moving to mmWave spectrum, we unlock much larger bandwidths, enabling compact satellites and high-gain antennas in devices that fit in your pocket. These high-frequency bands open up new possibilities: high-speed satellite-to-phone connections, satellite-to-vehicle links, and reliable, long-range drone-to-satellite communication. To realize our vision for 6G NTN, QSat-1 will be launched in 2026, a satellite designed by Qualcomm Technologies to support mmWave bandwidth over 200 MHz. Today, we are demonstrating live satellite-to-handset connectivity using an active in-orbit satellite with lower bandwidth. This is the first ever direct mobile mmWave NTN link, showing the real potential for global cellular coverage. In this demonstration, we are using a picosat transponder mounted on a D-orbit satellite. It operates over a 700 kHz bandwidth, receiving signals at a 29.5 GHz carrier frequency from our ground station, then transmitting using a band pipe configuration at 19.7 GHz to our handset. All results here are extrapolated to a 200 MHz bandwidth, which will be showcased in our upcoming QSat-1 demonstration. Because the satellite is in low Earth orbit, we rely on the NSL-COM ground station's precise tracking to maintain a stable feeder link. On the receiving end, we have developed a specially upgraded handset that captures high-quality signals in these bands, all while keeping the familiar smartphone form factor. This handset features an array of 8 dual polarization patch antennas and supports both fully digital and hybrid RF architectures. It can connect with any satellite above 20 degrees elevation, ensuring uninterrupted service by maintaining visibility to multiple satellites. At our operations center, we are showcasing the world's first mmWave direct satellite-to-handset communication link. Once the satellite rises above 20 degrees elevation, the handset starts receiving the signal, enabling data transmission from space. At peak elevation, the handset achieves an extrapolated data rate of 144 megabits per second, with a spectral efficiency of 0.7 bits per hertz. Throughout the satellite's orbital path, a stable throughput exceeding 40 megabits per second is maintained, whether the handset is stationary or moving. These results are groundbreaking. Imagine a future where any phone anywhere in the world can receive data at hundreds of megabits per second. That's our vision for 6G NTN, and today's demonstration is the first step toward making it real. In our second demonstration, we simulate the channel conditions of QSat-1 inside a large RF chamber. This critical step helps us verify the next generation waveform for even better performance. Our setup features QSat-1 under simulated channel conditions, created using a Ka-band channel fader and a 2-axis robot. A mini ground station transmits at 29 GHz to QSat-1, which then shifts the signal down to 90 to 20 GHz for a band pipe model to transmit directly to the handset mounted on the robot. The handset intelligently directs its beam and compensates for Doppler shifts, without needing to know the satellite's exact position. As a result, the user equipment streams video seamlessly. If a hand blocks the signal, the video freezes, demonstrating real-world effects. Throughput exceeds 140 megabits per second across two 100 MHz carrier components, matching the performance we expect from QSat-1 in orbit. These breakthroughs pave the way for fast, reliable connectivity virtually anywhere, powered by mmWave 6G NTN technologies across Ka and Q spectrum bands. Future smartphones and devices will unlock this potential, so stay tuned for more on NTN innovations.